Welcome back, focused learners, to another explainer. Today, we're breaking down the absolute foundation of telecom and networking. If you've ever connected to the internet, which obviously you have, you've relied on this underlying system. But how exactly does it work under the hood? Okay, let's dive into this. Introduction to IP addresses, your digital home address. Ever wonder how your smartphone manages to find one specific website out of literally billions? I mean, just picture this massive, chaotic, global network grid for a second. We've got smartphones, wireless printers, laptops, huge corporate servers, all lighting up, all trying to communicate at the exact same time. It sounds like a total logistical nightmare, right? So, how does one tiny packet of data know exactly where it's going without getting completely lost in the digital void? Well, the answer to that absolute chaos is the IP address. It's basically a unique identifier for absolutely every single network device out there. Whether we're talking about your PC, your phone, or that stubborn office printer, they all need one. You can think of it exactly like a digital home address or a phone number that lets these devices find and talk to each other across the globe. Because without an IP address, your device is completely isolated. It's essentially just sitting in the dark, entirely off the grid, totally unable to reach out to anyone. So, the crucial point is no IP equals no data transmission, period. This is a fundamental, unbreakable rule of telecom and networking. Without this unique identifier stamped onto your hardware, you literally cannot send or receive a single byte of data. It's the absolute bedrock of connectivity. No internet, no emails, no streaming. None of the good stuff works without an IP. Section 1. Inside the IPv4 structure. Now that we've nailed down exactly why these addresses are so essential, let's zoom in on the micro-level constraints that actually make this massive system work. Take a look at 192.168.1.10. This right here is a classic, standard IPv4 address. Honestly, if you've ever poked around your home router's settings, you've probably seen something that looks exactly like this. Notice the format, though. It's not just some long, random string of digits jumbled together. It's very specifically structured as numbers separated by periods or dots. 4. That's the magic number to remember here. The address is always, without exception, broken down into exactly 4 distinct blocks. In the telecom and networking world, we technically call these separate blocks octets. So every single standard IP4 address you're ever going to come across will have exactly 4 of these octets, neatly separated by those dots. 255. Now, this is a strict mathematical constraint of the entire system. Each one of those 4 numbers, those octets we just talked about, ranges strictly from 0 up to 255. You will never, ever see a standard IPv4 address with a number like 300 or 999 in it. No way. The dials on this system only go from 0 to 255. That is the absolute hard limit per block. Section 2, network part versus host part. Let's move to and see how this builds. Because those numbers aren't just random digits thrown together. They're actually divided into 2 critical, distinct sections. And this division is the real secret to how data routing happens. And this brilliantly illustrates the core logic of the entire system. We split the address right into the network part and the host part. The network part identifies the specific network you're on. Think of this exactly like your street name. Then, the host part identifies your specific device on that network. Think of that as your unique house number. Just like a postal worker needs both your street name and your unique house number to drop off a physical package, the digital network needs both of these parts to deliver your data correctly. But wait, how does your computer actually know which of those 4 numbers make up the street and which numbers make up the house? Well, that is where the subnet mask comes into play. By definition, a subnet mask determines exactly where the network ends and the host begins. It's basically the technical tool that draws the line in the sand. It tells the system, okay, look, these first few octets represent the street name, and this remaining number over here represents the specific unique house. Section 3, real-world field application. Okay, theory is great and all, but let's shift gears for a second. Let's step into the shoes of a field technician and apply this to some practical troubleshooting. Now, what's really interesting to see here is how this plays out with actual hardware. Imagine we have 2 laptops, laptop A and laptop B, sitting side by side on the exact same network. Check out their network prefixes. Laptop A has the prefix 192.168.1, and laptop B has the exact same prefix, 192.168.1. Because they're on the same network, they absolutely must share that identical network part. It's the host ending that changes. Laptop A is .10 and laptop B is .15. So the street they live on is exactly the same, but the houses themselves are totally unique. And that brings us to a really crucial diagnostic process that techs use literally every single day. Step 1, check the network prefix. Step 2, ensure those first 3 octets match for devices that are supposed to talk locally on the same network. And Step 3, verify that the last number is completely unique. You can consider this simple 3-step logic your secret weapon. It's basically a pro tip for mastering network setups and avoiding messy data collisions. Because think about it, if 2 devices accidentally had the exact same host number, the network wouldn't know which laptop gets the data, and the whole transmission would just fail. Master this, and you're well on your way to mastering network troubleshooting. You now understand the vital 4-octet anatomy of the IPv4 structure, what the subnet mask actually does, and why every single device needs its own unique digital home address to function. But I want to leave you with one final provocative thought. We know what happens when the host number changes, but if even a single digit changes in that network part, where does your data really end up? It's no longer on your local street, so how does the global internet actually find it? Well, that is a fascinating question about complex routing that we will definitely tackle in a future explainer. Until then, keep learning and keep focusing on those fundamentals.